We are now going to see fault bent fold, and in the next slide the fault propagation fold. The ideas are required in order to do successful cross section balancing. What happens in a fault bent fold? Consider layer rocks, and now also consider the fault plane which is going to strongly activate. That means, there is a weak zone considered from here to here parallel to the layer, and then from here to here at an angle to the layers, and again from here to here parallel to the layers. So, that this portion is a flat, this portion is a ramp, and this portion is a flat. Now, apply little shear, it produces kink band. Here kink folds are seen, straight limb and sharp hinges, all the layers are displaced. Therefore, one can define the kink axis in this way. When the kink band was developing here, where the flat ends and the ramp starts, here also interestingly where the ramp ends and the flat starts, the kink bands were produced. So, the kink axis, this can be called as stage 1. In the next stage or after some time instant, stage 2, where more movement has taken place along this fault, we find the kink fold is more profoundly developed within the hanging wall block. A few terms can be defined. This part is a syncline, so also this part, and this portion can be called as an anticline. As this is a tectonic transport direction, that is the foreland side and this side is the hinterland side, we define the term forelimb towards the foreland side of the folded layer within the hanging wall block, and the back limb towards the hinterland side within the folded layer of the hanging wall block. We observe that the back limb of the hanging wall anticline dips more gently than the forelimb. What does this mean? This is the dip of the forelimb, whereas here this is the dip of the back limb. If this angle is theta 1, this angle is theta 2, then theta 1 is more than theta 2. In other words, the back limb of the hanging wall anticline dips more gently than that in the forelimb. Back limb of the hanging wall anticline is parallel to the ramp. Back limb and here the layers are parallel to the ramp. This is the ramp. From here we can say that the dip of ramp is equal to the dip of back limb. Also, their dip directions are same. Axial trace B dash terminates at the ramp. This is the axial trace B dash, and that has terminated within the ramp. Actually, this one particularly is at the ramp flat contact. Not just that B dash, but other axial traces such as A and B. This one terminates at the flat and this one terminates at the ramp and flat contact. So, in the mature stage of movement, for a fault bent fold, one of the axial traces pass through the ramp flat contact. So, also in the mature stage, the axial trace passing through the ramp and flat contact can clearly be demonstrated. So, these are B dash and B. What about A and A dash? These two entirely terminate on the flat. Next important point, the axial trace bisects the interlimb angle of the fold. Let us take this particular top layer. These two I have drawn over here, and there is the axial trace A. This statement says that these two angles are the same. We can call gamma 1 and gamma 2. Not only this, for A, Same thing holds true for B dash, these two angles are the same, and for B these two angles are the same, and here these two angles are the same. As here gamma 1 equal to gamma 2, obviously these two angles alpha 1 and alpha 2 will be the same. This angular relationship becomes very important when we are going to extrapolate fold geometry by kink method or straight deep domain method. Now, if we look at the progressive evolution of the fault bend fold, not all the axial traces are fixed, not all the axial traces are migrating. This one is the fixed axial trace. You can see B and B, it in the intermediate phase and also in the advanced phase passes through the contact between the ramp and flat. Whereas, B dash, the axial trace climbed up and has come over here, and with an advancing time has come over there. That is why it is written as a migrating axial trace. What about A and A dash? Now, you can compare with figure B and figure C and decide. Now, let us look at the other variety of folding in association with ramp and flat, and it is called fault propagation folding. In this case, rather than ramping from one flat to another, this was the case in the fault bend fold. This was ramping from one flat to another, which was the case with fault bend fold. In case of fault propagation fold, that does not happen. What happens here? The fault dies out upward into axial surface of a syncline. This is the fault tip and this has not reached the surface. So, we can call this at this position as a blind fault. This is the blind fault. The blind fault is layer parallel. So, this is the flat and it has slightly cut the layer. So, this portion can be called as the ramp. So, here clearly the geometry of the fault plane is not a flat joining ramp and then ramp joining flat. This is not the case, rather only flat and then ramp. This is the meaning of this statement. This is the example of a blind thrust, but with time if the slip continues and from stage A we come to stage B, we find that the tip of the blind fault has migrated towards the earth surface. Consider this as the earth surface, we can clearly see that it has migrated. In other words, the length of ramp has increased here. As a result of this, clearly we can see that the folding has become more pronounced. Clearly, if I compare with this fold and that fold, I can say that here folding has become more pronounced. And as you see, this imaginary line has moved. So, this much is the displacement of the line. Now, the kink fold geometry can be seen in figure B if I trace this top layer. So, here we can say that the fault tip is accommodated by folding. This is the meaning of the statement. Here the back limb dips more gently than the fore limb. Where is the fore limb and where is the back limb? For that, let us come to figure C. As I see, the slip is in this direction, the tectonic transport is in this direction. This is the foreland direction and this is the hinterland direction. So, this limb of the fold can be called as the fore limb, and towards the hinterland direction, the other limb of the fold, I have tracked a layer, is called the back limb. Now, which one is dipping steeper, fore limb or back limb? Clearly, fore limb is dipping at steeper angle than the back limb. In other words, the back limb dips more gently than the fore limb. For example, if I find the dip over here, this is almost 90 degree, whereas here this is certainly an acute angle. So, if I call this theta 1 and this as theta 2, theta 1 definitely as per diagram is more than theta 2. So, this sentence is explained. Dip of the back limb equals the ramp angle. What is the ramp angle or the ramp dip? this is the ramp and this is the dip phi. Phi equal to theta 2 clearly within the diagram. So, dip of back limb equals a ramp dip. We can compare statement 3 and 4 for the fault propagation fold with the equivalent statements for the fault bend fold. Back limb dips more gently than the fore limb, which is explained here. What happens in this case? Here also the back limb of the hanging wall anticline dips more gently than the fore limb. Again I can demonstrate. So, this is the dip of the fore limb and this is the dip of the back limb. Then between theta 1 and theta 2 I can find theta 2 is less than theta 1. So, this is same for both fault bend fold and the fault propagation fold. Dip of back limb equals a ramp dip. This is also the same. Here we see that the dip of the ramp, say it is phi, phi is equal to theta 2. Next statement, the box fold reduced to chevron fold towards their course. If this is a fold being drawn, the outer layer is known as extrados and the inner layer is known as the intrados. This portion of the fold is called the core of the fold. So, if I draw a syncline, this portion is the core of the fold. If I draw almost a recumbent fold, then this is the core of the fold. This is the meaning of the term core. Now, let us try to understand the statement box folds reduced to chevron folds towards their course in this diagram. Let us track this fold. Here I am getting two hinge points marked by circles, whereas if I go towards the core of the fold, where is the core? This is the core of the fold. I find that here the fold has a single hinge point. So, a box fold with two hinge points reduced to a chevron fold at the core. The fold geometry changes as one goes from the fold's periphery towards the core. This is the meaning of this statement. And because of that, we see one more thing, that the axial traces drawn for the box fold actually merge and become a single axial trace. Here it is a single axial trace, as if from here bifurcation into two axial traces have taken place. When we do the kink method of fold reconstruction in advanced stage, I will show you some diagrams where such a situation indeed happens. That is why we are developing concepts before getting into the actual cross section balancing problems. Axial trace bisects the interlimb angle of the fold. Let us take this axial trace and the interlimb, and as per the diagram the interlimb angle has been bisected. This is the place when is a single axial trace, but when we look within the box fold regime, here the box fold, true box fold regime, here also the same thing happens. These two angles are the same and these two angles are the same. So, this statement is true for the box fold portion and also for the chevron fold portion. Just want to explain the basic. Chevron fold is same as the kink fold, that is a fold with straight limb and sharp hinges, such as this geometry. A fold with straight limb and sharp hinges. Be very clear that point number 6 also holds true for a fault bend fold. Axial trace bisects the interlimb angle of the fold, but box fold reducing to chevron fold does not happen in case of a fault bend fold. Here I am getting a fold with two hinges and that is continuing within the core of the fold also. So, the box geometry is persisting within the core of the fold for a fault bend fold, which is not the case for a fault propagation fold. That means, there are certain common points between fault propagation fold and the fault bend fold. Let me emphasize, in case of a fault propagation fold, the fault propagates with time from bottom towards top, whereas in a ideal fault bend fold model, we are thinking of a pre-existing weak zone parallel to the layer, at an angle to the layer, and again parallel to the layer, and then shear happening. I have referred the terms ramp and flat, and we need to understand their relationship with the competency of the rock also. Consider there is a basement rock shown by these crosses, and basement rock is showing a regional dip in this direction. Consider there is a limestone and shale alteration developed on the basement. Shale layer is showing bedding planes shown by these dashed lines. Suppose sigma 1 is the compressive stress that acts on this rock. Compressive stress at great depth in the ductile regime at more than 8 or more than 15 kilometer can produce folding, whereas in shallow crustal depth less than 8 kilometer, sometimes less than 15 kilometers can produce faulting, and due to compression we would expect reverse faults. Consider that flat and ramp geometry are produced. Flat is shown in this place and the ramp is at an angle, and again the flat and then followed by the ramp. Flat is defined parallel to the bedding plane of the shell. Flat develops parallel to bedding planes of shell, and for when the fault passes through limestone, which is a stronger rock unit, it develops a ramp. Now, what has been explained in terms of limestone as stronger rock than shale, it can have any other rock A and B. One is difficult to deform and another one is easier to deform, or A is stronger rock and B is a weaker rock. In that case, even under the same compressive regime sigma 1, the fault plane can have step like geometry producing ramp flat, ramp flat. Consider the angle between the flat and sigma 1 stress is alpha 1 and the angle between the ramp and sigma 1 stress is alpha 2. Then in this case alpha 2 is more than alpha 1. Another angle step up or cutoff can be defined given by theta. What is that? It is the angle at which the ramp steps up from a bedding. Here I have already said these lines represent bedding. So, if I extrapolate it here, this is the line and the ramp steps up here, this angle is theta. Cutoff word was used earlier to explain cutoff point or cutoff lines, but here the word cutoff has a completely different meaning. Here they were representing points or lines, whereas here cutoff or step up theta is the angle. This theta angle depends on the pore pressure and the rock types. Pore pressure has great control on the rock's strength. Pore pressure controls rock strength. Just to recollect, when we are presenting the term strength of rock, a good representation can be the Young's modulus of the rock. After defining the step up angle theta or the cutoff, we can say that the step up angle theta is measured with respect to the regional dip and not the horizontal, because as you see in the diagram, this is non-horizontal line and is actually representing the regional dip. What about this angle? This angle is not theta, this is a horizontal line. So, the regional dip can be given by this angle phi, whereas theta is the step up angle or the cutoff angle. While studying the basics of thrust belts, let us visit the concept of the bow and arrow rule. It says that the slip perpendicular to fault strike is approximately 10% of the fault length. What is the fault length? Suppose from this point A to point B the fault is exposed. I can join AB by a straight line. This L represents the fault length. Tentatively we can say that slip perpendicular to the strike S is equal to KL, where K is nearly 10%, but from fault to fault it can vary from 7 to 12%. Note that we are not talking about net slip, rather slip that is perpendicular to the fault strike. Consider this case, the block diagram. Here this is the net slip. We can resolve net slip into two components, the strike slip and the dip slip. The dip slip component I can draw here. This dip slip can be resolved into two components, the throw and the heave. It looks like from the statement slip perpendicular to the fault strike is H. Note that the fault strike AB is perpendicular to H direction. So, it looks like they are talking about heave of the fault. A quick recapitulation: if theta is the dip of the fault, then this angle is also theta, then we can write that tan theta is equal to T divided by H, also T square plus H square is equal to D square. Also from the triangle that is drawn on the fault plane, we can write A square plus D square is equal to N square, N is the net slip. From these two equations we can write down N is equal to square root of T square plus H square plus A square.